Hello guys, welcome back to the Universe of Tech Up. In this tutorial, we will learn about Bellman-Ford algorithm. First, we need to learn what is Bellman-Ford algorithm and why it is used and key features of Bellman-Ford algorithm. Start with the context. The Bellman-Ford algorithm is a well-known algorithm used to find the shortest paths from a single source node to the all other nodes in a weighted graph. Unlike Dijkstra's algorithm, Bellman-Ford can handle a negative weights and also detect a negative weight cycles. And this is what is Bellman-Ford algorithm. The Bellman-Ford algorithm is a graph search algorithm that computes the shortest path from a single source vertex to all other vertices in a unweighted graph. Unlike Dijkstra's algorithm, it can handle the graphs with negative weights edge. Next, why we need to use this Bellman-Ford algorithm. It's used when you need to find the shortest path in a graph where the edge weights could be negative. Also, it's the only algorithm that can detect. So we need to learn why it is used in Bellman-Ford algorithm in shortest path. It is also detects the it also find the negative weights and also it's only algorithm that can detect the negative weight cycles. And negative weight cycles are special case where the total weight of the cycle keeps decrease as you traverse it. This is why we need to use Bellman-Ford algorithm. Next, we move on to the application of Bellman-Ford algorithm, where we need to use applications of Bellman-Ford is shortest path problems. Like when we have a graph with negative edge weights, the Bellman is the go to the algorithm. And next is the arbitrage detection in currency exchange, like that. In finance, if there is an arbitrage opportunity in currency exchange rates, negative cycle in the graph of exchange rates, Bellman-Ford can detect it. Next, another one is routing algorithm. In a computer networks, the algorithm can help in routing where certain edges might have negative weights like bandwidth, cost, or delays, like that. Next, and also used in game development, graph analysis, like that. In graph analysis, for analyzing a graph that may contain a cycle with negative weights, so that's also we need to use it in the Bellman-Ford algorithm. And also use it in game development field, we need to use the Bellman-Ford algorithm. Next, we move on to the Bellman-Ford algorithm. Before we go into Bellman-Ford algorithm, we need to learn key features of Bellman-Ford. It handles the negative edge weights and detects the negative weight cycles in the graph and not an efficient as Dijkstra's algorithm in most cases since it runs as but very versatile. Next, Bellman-Ford algorithm. The algorithm's working principle step-by-step breakdown. First, we need to initialization. Set the distance to the starting node to 0 and all other nodes to infinity. In coming example, we need to show how Bellman-Ford algorithm works in graphs. Next, relaxation. For each vertex, repeat the following for a total of v minus 1 times, where v is the number of vertices. For each edge, u comma v with weight w. If the distance to u plus w is less than the distance to v, update the distance to v. This is the relaxation step. Next, the negative cycle detection. Perform a one or more iteration over all edges. If any distance can still be updated, a negative weight cycle exits. This is negative cycle detection steps. Next, returns the result. Returns the shortest path distances from the starting node to all other nodes. These are all the steps for Bellman-Ford algorithm. Next, we take one example to show how Bellman-Ford algorithm works. The Bellman-Ford algorithm is find the shortest path from a single source node to all other nodes in a weighted graph. It can handle a negative edges weight and also detect a negative cycles. We all know about Bellman-Ford algorithm. Key features of Bellman-Ford is it handles the negative edge weights, detects the negative weight cycles in the graph. For example, I am taking a graph. These are all the nodes. This is A, this is B, This is C and this is D. The A to B, we need to connect A to B. The weight A to B weight is 1 and B to C weight is minus 2 and C D to C is D to C is 3 and B to D is 4 and A to C is, this is the graph I take. The adjacency list of A is, the adjacency list of A is B comma B to A to B and A to C. A to B weight is 1 and A to C weight is 4. Next, the B adjacency are B to D and B to C. B to C weight is minus 2 and B to D weight is minus. B to D is 2 and C neighbors are C to D is 3. This is a graph and the edge list are A comma B comma A to B is weight is 1 and next A to C A comma C comma A to C is 4. Next B to C. Next B to D. B comma D comma 2. B to D weight is 2. Next this 2. Next D to C. D comma C is 3. D to C weight is 3. This is the weights of the edge list. Next, first we need to initialize the nodes. Nodes. Next one is word. First one is A. Next one is B. The next one is C. Next one is D. And first we need to initialize A is equal to 0 in all or infinity. Comma V comma W. What is U? U is the starting node, V is the ending node and W is the weight. General formula for relaxing edge is the distance of V is equals to minimum dist comma distance of U plus distance of W. Distance of W. This is the formula for relaxing edge. A relaxing edge formula. Relaxing edge formula. This is the relaxing edge formula. Next, what I need to do is, next, first iteration 1. We need to consider iteration 1. Iteration 1. The first I need to take edge A to B. A to B. The weight is equals to 1. The weight is equal to 1. The current distance to A to B is 1. So the distance is equal to 1. The B weights are infinity. The vertex initializes to infinity. The distance to B is, for A is distance A plus 1 is equals to, distance of A is equal to 0 plus 1 is equals to 1. This is the distance of A. Next, I need to take distance of B plus 1 is equals to, distance of B is equal to infinity. So is equals to plus 1. So answer is 1. Distance formula is distance of B is equals to minimum of, I need to substitute this formula, minimum of distance of V is, it means B is infinity, 1. So the answer is 1. This is the iteration 1. Next I need to take edge A to C. A to C. The weight is the weight is 4. What I need to do is distance of A plus 1 is equal distance of C plus 1. No, no. Distance of A plus C. Distance of A plus weight. Right? So, distance of A is equals to 0. 0 plus 4 is equals to 4. 4 is the answer. Next, we need to substitute dict is equals to dist is equals to C is equals to minimum of the C is infinity, right? The C is infinity. The weight is 4. The infinity comma weight is 4. This is the new distance. Next, I'm taking edge B to C. C. The weight is like minus 2. B to C is minus 2, right? Yes, B to C is minus 2. What we need to do is distance of B edge is the 1 plus minus 2. The 1 plus minus 2 is equals to minus 1, right? Minus 1. So, next we need to substitute in the distance of 4 comma 4 comma minus 1. 4 comma minus 1 is equals to is the minus 1. Next, so the new distance to C is minus 1. So the new distance of my new distance is the new distance. Next, we move on to the H B to D is 2. The current distance is equal to distance to D through a B is 1. 1 plus the D is 2 is equals to 3. This is the distance to D through B. Next, we need to calculate distance of D comma infinity comma 3 is 3. New distance. So, the new distance is 3. New distance. This is the new distance. Distance, right? Next, the edge D to C. D to C. The weight is 3 plus 3 is 6. We need to calculate minimum distance. Relaxation distance. C is equals to comma minus 1 comma 6. That is, the minimum is minus 1. So, you take minus 1. So, the distance to remains is minus 1. No update because minus 1 is already smaller than 6. After the first iteration, we need to update these distances. The distance is, we need to take a tables. A, second one is B, and third one is C, and third one A to A is 0. A to A is 0. A to B is equals to 1. And A to C is equals to minus 1. Next one is B is equals to 1. A to C is equals to 4. And B to C is equals to minus 1. And B to D is equals to 3. And D to C is equals to minus 1. The last is 3. Next, iteration 2. Iteration 2. Relaxing edge again. At this point, we check if any further updates are possible. The key here is that if the distance to a vertex does not change during this iteration, it means the shortest path to that vertex has been found. The edge A to B is the edge A to B. The distance is equals to 1. So 0. 0 plus 1 is equals to 1. So we need to calculate distance of B is equals to minimum of 1 comma 1 is equals to 1. This is the minimum. No updates because the distance remain 1. It is already the minimum. Next edge is A to C. A to C. The current distance to C is minus 1. So distance of 0 plus C is equals to minus 1, right? Minus 1. The answer is equals to the distance of A to C is updated distance of A to C is 4, right? We need to take 4, not minus 1, 4. So answer is 2. Update because distance of C minimum of minus 1 comma 4. The minimum is minus 1, right? The minimum is minus 1. So no update because the distance remains minus 1. It's already a minimum. So next we need to take edge B to C. B is 1. 1 plus C is B to C is minus 2 equals to minus 1. Next we need to find the minimum distance. So minimum of minus 1 comma minus 1 is equals to this is minus 1. So no updates because the distance remains minus 1. It is already minimum. B to C is minimum. Next we need to take H B to D. B to D. The B to D is 1 plus 2. 1 plus 2 is equals to 3. The edge of next is equals to 3. So what we need to do is we need to calculate minimum distance. Distance of equals to minimum of 3 comma 3. It is 3. This is no update because the distance remains 3. It is already the minimum, so no need to change. Next we need to take edge D to C. Distance is equal to 3. 3 plus 3 is equals to 6. So we need to find minimum distance. We need to find minimum distance of C is equals to minimum of minus 1 comma 6. So the minimum is minus 1. No update because the distance remains. It is already the minimum. The iteration 1 and 2 should already be the correct shortest path. The remaining iteration, next we move on to the iteration 3. This is a relaxing edge again. Iteration 3. We need to take edge A to B. The weight is 1. So 0 plus 1 is equals to 1. We need to calculate distance of B minimum of 1 comma 1. Next we need to take C. The weight is 4. The weight is 4. The current distance to C is equals to minus 1. Distance to C through A. Distance of A to C, A plus 4. A means 0. 0 plus 4 is equals to 4. We need to find minimum distance. So distance of C is equals to of minus 1 comma 4. It is minus 1. This is the minimum distance, right? No update because the distance to C remains same. Minus 1 is the still minimum. Next, need to take edge B to C. B to C, the weight is minus 2. 1 plus minus 2 is equals to minus 1. We need to calculate distance minimum. Minimum of minus 1 comma minus 1 is equals to minus 1. No update because the distance to C remains the same. Minus 1 is the still the minimum. So next we need to take edge B to D. The weight is 2. 1 plus 2 is 3. Distance of D is equals to minimum of 3 comma 3. That is 3. The edge of D to C is the weight is equals to 3. So 3 plus 3 is 6. So we need to calculate minimum distance, that is distance of C equals to minimum of minus 1 comma 6. The minimum is minus 1. No update because the distance to C remains the same. Minus 1 is still the minimum. Final result after iteration 3, no changes have been made to the distance during the iteration 3, indicating that the shortest paths have already been determined in previous iteration. Therefore, iteration 3 does not alter the values. Notes vertex is equals to, this is the final iteration. A is equals to 0, B is equals to 1, C is equal to minus 1, D is equals to, this is the final iterations. The Bellman-Ford algorithm runs to the V minus 1 iteration. V is the number of vertices in the graph. Graph 4 vertices, V minus 1 is 4 minus 1 is equal to 3. There are 3 iterations in the graph. The iteration 1, the distance were updated from B, C and D. The iteration 2, further updates occurred for C but no changes for other vertices. In iteration 3, no updates were needed. So the algorithm is terminates. The final distance or the shortest path from the A to all other vertices. Distance from A to A is 0 and distance from A to B is 1 and distance from A to C is minus 1 and distance from A to D is minus 1. This is all about Bellman-Ford algorithm. Next, we move on to the implementation of using a Python programming language. Start by initializing a dictionary list where the keys are the vertices from 0 to v minus 1 and the values are initially set to infinity, float information, info, infinity, and except for the starting node and list of start which is set to 0. This step ensures that the source node start with a distance of 0 and all other nodes start with the infinity distance. We move on to the implementation. First, we need to define Bellman-Ford graph and V and start as the parameter. These are the parameters. It initializes the distance from the start to all other nodes as infinity. What I need to do is next we need to the distance is equals to V the float of infinity for V in range V. Next the distance of start equals to 0. Next, we move on to the relaxation edges. The next step is to relax all the edges in the graph v minus 1 times, where v is the number of vertices. Relaxation means trying to reduce the distance to a vertex by finding a shorter path through its neighbor. For each edge u, v, weight in the graph, if the distance to vertex u plus the edge weight is less than the current distance to vertex v, the distance to vertex v is updated. Next, we need to take for loop for in range v minus 1 v minus 1 for underscore in range v minus 1 for u v weight in graph if the distance of u plus weight is less than distance of v. Is true. Distance of v is equals to distance of u plus weight. The negative cycle, next one is negative cycle detection. In this, we need to detect a negative cycle relaxation steps. The algorithm checks all the edges one or more time. If any distance can still be reduced, this means the graph contains a negative weight cycle and the algorithm reports it. If no such changes occurs, it means there are no negative cycles. Next, we move on to the negative cycle detection for u, v, weight in graph if distance u plus weight is less than distance v. Print the graph contains negative weights. The graphs అంటే negative weight cycle. Otherwise return none. The output the shortest distance is if no negative cycle is detected, the algorithm returns the dictionary dist which contains the shortest distance from the source node to all other nodes. Finally, the distance are printed to the console. If if distances print the shortest distance print shortest distance from node comma start node for node in range v print the distance to node is distance to node is distance of node. Next we need to write the graph. The graph is equals to flower bracket. This is the way 0 comma 1 comma minus 1 and 0 comma 2 comma and 1 comma 2 comma 3 1 comma 3 comma 2 1 comma 4 comma 2 and 3 comma 2 comma 5 3 comma 1 comma 1 4 comma 3 comma minus 3. The first one is u v w. U is the starting node, v is the ending node, and w is the weight. This is the graph I need to take. We need to run this code. The distance to node is equals to 0 to 0. Distance to node 1 is equals to minus 1. The distance to node 2 is equals to 2. Distance to node 3 is minus 2. Distance to node 4 is 1. This is the Bellman-Ford algorithm. If you like this video, please don't forget to subscribe, like and share and comment in this video.